Setting up a controlled experiment. An experiment in which only one variable is manipulated at a time is called a controlled experiment. You decide to test the crickets at 3 different temperatures: 15 degrees Celsius, 20 degrees Celsius, and 25 degrees Celsius as shown in Figure 3. Those are the 3 people down below. All other variables are kept the same. Otherwise, your experiment would have more than one manipulated variable. Then there would be no way to tell which variable influenced your results. Experimental bias. In any experiment, there is a risk of introducing bias. For example, if you expect crickets to chirp more at 25 degrees Celsius, you may run experiments at just that temperature. Or, without meaning to, you might bias your results by selecting only the crickets that chirp the most often during to test. Having a good sample size or the number of crickets tested is also important. Having too few crickets may bias your results because individual differences exist from cricket to cricket. So, a controlled experiment. The manipulated variable in the experiment below is temperature. Design experiments. In the boxes, write the number of crickets you would test for this controlled experiment. On the lines below, write 3 other variables that must be kept the same. Collecting and interpreting data. You are almost ready to begin your experiment. You decide to test 5 crickets, 1 at a time, at each temperature. You also decide to run multiple trials for each cricket. This is because a cricket may have differently from one trial to the next. Before you begin your experiment, decide what observations you will make and what data you will collect. Data are the facts, figures, and other evidence gathered through qualitative and quantitative observations. To observe your data, you may want to make a data table. A data table provides you with an organized way to collect and record your observations. Decide what your table will look like. Then you can start to collect your data. After your data has been collected, they need to be interpreted. One tool that can help you interpret data is graph. Graphs can reveal patterns and trends in data. Sometimes there is more than one interpretation for a set of data. For example, scientists agree that global temperatures have gone up over the past 100 years. What they do not agree on is how much they are likely to go up over the next 100 years. So, in the sequence part there, underline and number the steps involved in collecting and interpreting data. In the do the math, a data table helps you organize the information you collect in an experiment. Graphing the data may reveal any patterns. Read graphs. Identify the manipulated variable and the responding variable. Number 2, read graphs. As the temperature increases from 15 to 25 degrees, what happens to the number of chirps per minute? Number 3 is predict. How many chirps per minute would you expect when the temperature is 10 degrees? Next, page 24. Drawing conclusions. Now you can draw conclusions about your hypothesis. A conclusion is a summary of what you have learned from an experiment. To draw your conclusion, you must examine your data objectively to see if they support or do not support your hypothesis. You also must consider whether you collected enough data. You may decide that the data support your hypothesis. You conclude that the frequency of cricket chirping increases with temperature. Now, repeat your experiment to see if you get the same results. A conclusion is unreliable if it comes from an experiment with results that cannot be repeated. Many trials are needed before a hypothesis can be accepted as true. Your data won't always support your hypothesis. When this happens, check your experiment for things that went wrong or for improvements you can make. Then fix the problem and do the experiment again. If the experiment was done correctly the first time, your hypothesis was probably not correct. Propose a new hypothesis that you can test. Scientific inquiry usually doesn't end once an experiment is done. Often, one experiment leads to another. In drawing conclusions, sometimes the same experiment can have very different data. So, number 1, look at the data in the table. Do the data support the hypotheses that crickets chirp more in warmer temperatures? Explain. Number 2, if the data in this table were yours, what might you do next? Explain. Number 3, can you draw a conclusion from this data? Why or why not? Communicating is the sharing of ideas and results with others through writing and speaking. Scientists communicate by giving talks at scientific meetings, exchanging information on the internet, or publishing articles in scientific journals. When scientists share the results of their research, they describe their procedures so that others can repeat their experiments. It is important for scientists to wait until an experiment has been repeated many times before accepting a result. Therefore, scientists must keep accurate records of their methods and results. This way, scientists know that the result is accurate. Before the results are published, other scientists review the experiment for sources of error, such as bias, data interpretation, and faulty conclusions. Sometimes a scientific inquiry can be part of a huge project in which many scientists are working together around the world. For example, the Human Genome Project involves scientists from 18 different countries. The scientists' goal was to create a map of the information in your cells that makes you who you are. On such a large project, scientists must share their ideas and results regularly. Come up with ideas for communicating the results of your cricket experiment in Figure 5. So, communication is the noun form of the verb communicate. Write a sentence using the noun communication. Figure 5. Since the Human Genome Project touched upon many areas of science, communication was important. Get together as a group. You don't have to do this one on page 25. Just skip over that part. On this page, in a scientist's shoes, how do scientists investigate the natural world? When you think like a scientist, you develop hypotheses and design experiments to test them. So, design experiments. Think like a scientist to find out which falls fastest. An unfolded sheet of paper, a sheet of paper folded in force, or a crumpled sheet of paper. Write down your question, your scientific attitudes involved, a hypothesis, the variables, the manipulated, the responding, factors to consider. Collect data, number of trials, unit of measure, scientific skills used, and next steps. Just do the question and hypothesis and variables for this part. What are scientific theories and laws? Sometimes a large set of related observations can be connected by a single explanation. This explanation can lead to the development of a scientific theory. In everyday life, a theory can be an unsupported guess. Everyday theories are not scientific theories. A scientific theory is a well-tested explanation for a wide range of observations and experimental results. For example, according to the atomic theory, all substances are composed of particles called atoms. Atomic theory helps to explain many observations such as why iron nails rust. Scientists accept a theory only when it can explain the important observations. If the theory cannot explain new observations, then the theory is changed or thrown out. In this way, theories are constantly being developed, revised, or discarded as more information is collected. A scientific law is a statement that describes what scientists expect to happen every time under a particular set of conditions. Unlike a theory, a scientific law describes an observed pattern in nature without attempting to explain it. For example, the law of gravity states that all objects in the universe attract each other. Look at Figure 7. So, according to the law of gravity, This parachutist will eventually land on Earth. Give an example of a scientific law. You are done now with this reading.